talk about distributed optimization via ADMM, alternating iteration method of multipliers. First, I will cover some background. We will see what is a dual ascent method and method of multipliers. Then we will see why we need ADMM, and then I'll try to cover some extensions of ADMM. First, dual ascent method. Consider an equality constraint convex optimization, minimization over x, minimization of f of x over x subject to ax equal b. X is of dimension n. We have an A matrix, it doesn't need to be a square matrix or anything. And we have an f function from n-dimensional space to n-dimensional space, and it is convex. Well, we all know that the Lagrangian for this problem, we can write it in this form. Y is the dual variable. And the dual problem is defined by maximizing some function g, which is defined this way. We won't use the definition of g, but I just put it here for the sake of completeness. G is defined as infimum of the Lagrangian over x, and you can show that by some mathematical equations. It is equal to convex conjugate of f, defined as f star by supremum of these equations, and you can write g as this. When you maximize g over y, then this is a dual problem, and assuming it's dual and assuming a strong convexity, we can see that the solution of dual problem and the original problem, primal problems, are the same. When f is strictly convex, we can find the optimal value by solving the dual problem, if we assume that it is strictly convex. Then this is the relationship. In dual ascent method, in order to find this solution, we solve this alternating approach. First, we minimize the Lagrangian over x, we fixed y. Let's start from iteration 1. We fixed y, which is usually 0. We find some k and then update dual variable by this. Alpha here is the step size of the dual ascent method, and you need to tune it manually. Well, I haven't worked in this area particularly. I don't know how we can tune this, but I just heard that this is very difficult to tune. So this is some problem with these kind of approaches. But we can show that this function increases in each iteration if we choose alpha appropriately. Therefore, we are maximizing g and actually we are minimizing the original problem. So this is dual ascent method. The problem with this approach, as I said, is to tuning alpha, the step size, and therefore, and one other problem is that one benefit of this approach is that you can use it in decentralized problems. You can use it for distributed networks over different nodes. For example, if we assume that the objective function is the sum of some separate functions fi, and we assume that we have a network of n different nodes, and each of the nodes has access to only its own objective function fi, and they have the same variable. They have some variable for each of them, xi of particular dimension, and this whole thing is called x. We can write the Lagrangian in this form. We write the matrix A as concatenation of some matrix A1 to AN. We can write AX as the summation. Therefore, the Lagrangian will be in this form. We can see it is separable in x, which means that, for example, you have n different minimization like this, and you can solve it particularly, and you can solve it separately in each of these distributed nodes. So this is one advantage. This is one of the advantages of dual ascent method. Here, just to mention that, if we are solving a distributed algorithm, the first part of this iterative algorithm can be solved separately. So this is minimization over xi, and this L is minimized over only xi. Therefore, you only have one of these terms in the summation, not all of them, only one. So you will have n different minimization in the first step of dual ascent, and then you have a dual variable update, which is using the whole ax. In order to calculate this, you need to have a center in your network, and you need to send all of the variables xi's to that center to calculate the peak x and a multiplied by a so that you can update your variable y. Now that you have updated y, then you will send back to the individual nodes. So in each iteration of dual decomposition method, you need a broadcast and a gather operations. And yeah, this is exactly what I just explained. Another approach is method of multipliers. I'm covering these two because ADMM is a combination of these two. Method of multipliers is similar to dual Lassam method. One difference is that we have another penalty term here. We define the augmented Lagrangian. Previously it was simple Lagrangian. Here we have augmented Lagrangian defined this way. And this row is called the penalty parameter. The augmented Lagrangian, we can see it as the Lagrangian of this function. When you write the Lagrangian for this function, you will just add a dual variable and multiply it with the constraint. So these two are actually equal because for any feasible x, then this part will be 0, so the solution of these two problems are actually equal. And yeah, therefore the associated dual function, we will define it as g of rho, which is the infimum of L of rho, because we have a rho parameter. The benefit of including a penalty term is that this Lagrangian will be differentiable under rather milder conditions. And if we apply dual Lassam method to the modified problem, we will see this, but here you see that here this is very similar to dual Lassam method in the sense that we have a minimization part and then dual variable update, but here the difference is that dual variable step size update is rho, and this rho is actually the penalty parameter, if you remember what we have here. So this is the only difference between method of multiplier and dual Lassam. Though this Lagrangian is also modified because we have one more penalty term. And another advantage of method of multiplier is that this f can take infinity value and doesn't need to be strictly convex. But in dual Lassam method, it needs to be strictly convex. So that's the advantages of adding a quadratic term in the Lagrangian. Yes.
The previous slide. Should rho be constant?
It is constant.
Oh, it is constant.
Yes, you will choose. Yes.
It can
constant.
be proved that it converges to the optimal point with the
Rho?
constant rho. Can we?
For ADMM, we will prove this.
No, for augmented Lagrangian.
Well, I don't know exactly, but
For
there should
constant,
be
yes,
proofs.
it would, but I don't think that it needs to be constant. I guess that the condition is
Because, for example, in the
diminishing a step size would work as well, I guess. If you want to run it iteratively, I guess. No? I guess that diminishing
I
step size
think the
would
only
work.
condition is like differentiability smoothness.
Yes.
Yeah, and of course that the problem is convex. Right?
Exactly.
does it converge exactly for any given
Yes.
epsilon?
Yeah, like a normal convergence. Yeah, exactly, like a classical convergence. So we set an
So you
epsilon.
say that it doesn't depend on rho. So, for
No,
example,
probably,
only if we grows the number of step size, then it converges
I guess rho should be positive.
okay,
yeah.
it converges as
It can be just faster. It needs less number of iterations if you increase the step size.
so. In the previous slides, there was some alpha k. No, previous.
Okay.
Yes, here.
Yes. Yes.
So can it be also a constant for?
Yeah,
This
it can be.
K?
Yeah,
Yeah, it can be. It doesn't
I think so, but
The
that
whole vector
Uh-huh.
of x. Is
Well,
that
that we will
applicable
see.
in that
That
case?
we will see in distributed scenario. We will have a constant here, xi, for every I equals some z,
Okay.
and you are minimizing over xi and z,
Okay.
Yeah.
and your constraint need to be equal for all of the i's.
Hmm.
So we will see that.
Okay.
Okay. KKT conditions for problem 1 are primal feasibility and dual feasibility. This is the gradient of the Lagrangian. Well, by definition, we know that xk plus 1 minimizes the Lagrangian. This was the first step of method of multipliers. So we can just write the gradient of the Lagrangian. You will see this. And now I define for my second step of the algorithm is that yk is equal to yk plus 1 is equal to yk plus this term. So you will see it here. Now you can replace it with yk plus 1. Now you see that this, actually the pair of xk plus 1 and yk plus 1 in this iteration is actually satisfying dual feasibility. So in every iteration we are guaranteeing that these two are whole. So that's the reason that we choose rho as step size. But it should be constant. I don't know if rho changes here. Then what will happen?
No, from nothing will happen here.
Yeah,
the optimality.
the corresponding
but then,
corresponding yk plus 1 will update. Yeah.
Yeah, exactly.
Nothing will change.
Okay. The advantages of method of multipliers, as we said, is that we can make it separable because dual assembly method is not useful for distributed scenarios. So dual assembly method can be used in this distributed scenario, but but method of multipliers cannot be used, and that's the reason that we switched to ADMM, because in this version, in this problem, we cannot solve distributed problem, but we have more general conditions of convergence. So in ADMM is an algorithm that is supposed to blend decomposability of dual ascent and convergence properties of method of multipliers. So we define this minimization problem to minimization of f and g over x and z, subject to a linear constraint. And we have these dimensions, x is of dimension n, z is of dimension n, and these things. And we assume that f and g are convex, and these are some definitions that we will use it. We assume the optimal value for this problem 2 is defined as p star, which is the increment of f of x plus g of z. We will use these definitions. Okay, we again form augmented Lagrangian. We have this constraint and dual variable and some penalty term, more as known to constraint, and some penalty parameter rho. ADMM consists of these three steps. First step is minimization over x, when you keep fixed the other two variables x, z, and y. Then you will update the value of x, you will minimize only over z. Then you will update the dual variable y, the same fashion that you do in method of multipliers, with the same step size. Now this is very intuitive and it seems that it should work, but we will see the proof. And just to make a comparison with method of multipliers, just consider we had this Lagrangian. Instead of ADMM is these three steps. We want to use method of multipliers method for this Lagrangian. What you will do is that, well, you have two variables, you have to minimize over x and z of L of rho. Then you will have an updated version of them. Then you will update to a variable y. Now, ADMM can be seen as this method of multipliers, just that the first step of method of multipliers is joint optimization over x and z, but that is an alternating optimization. So that's hence we have the term alternating direction method of multipliers called ADMM. And one other point that I want to mention is that separating this minimization, this joint minimization for each of them is exactly what allows us for decomposition and makes us able to solve distributed problems. This is one other scale form of ADMM that is much more used in practice. It's easier to remember. Let's define residual as this residual we want it to be 0 because this is a feasibility condition that we have. We can write these are the two terms in the Lagrangian. These are these two terms. Y times residual, rho over 2 times norm 2 of residual. This is exactly what we have. So we want to rewrite Lagrangian. We can write it in this way by making this square. And you define u as 1 over rho dual variable y. Then you can write the minimization problem in this fashion. The first step is the minimization over x. We will not see this term because we are minimizing over x, so we don't have u. You're only minimizing this term. This is the residual plus u, and you have rho over 2, and you're minimizing only over x, so you will not have g. The second one is very similar, but only over z. The third step, it was the minimization over was the updating over y. Now I have defined u as 1 over rho, so we will not have that step size here. So you can see that this u new to our variable is defined as the sum of the residual over the iterations. So you can see that if this algorithm is supposed to work, then u will not necessarily converge to 0 or anything. It will converge to the sum of this residual. But it should converge to something. For convergence proof, we will make some assumptions. First assumption is that we assume that function f is closed, proper, and convex. It means that the epigraph of the epigraph means the space above the function. For example, you have a function like this, and this is the epigraph somewhere here. This is space. It's called the epigraph of f. This is space. If it is closed, non-empty, and convex, then we assume this is the definition of closed, proper, and convex. Just to have an intuition. And yeah, I also want to mention that one of the advantages of ADMM is that we allow this f and g to be non-differentiable, and we assume that they can take the value of infinity. It's not a problem for this approach. And for example, f can be an indicator function over some convex set C, for which for the elements in C, the value of f will be 0. For the element outside of C, it will take the infinity. Just like, for example, you have a minimization problem. Minimization, the thing that I use very much in my research. Subject to norm for values of O less than some epsilon. Actually, you can form this guy as some other function g of O, and this g is indicator function for those elements that are inside this circle. Then that is 0, otherwise it is infinite. So second assumption is that Lagrangian L0, if you recall, is this Lagrangian without the penalty term. This is the meaning of L0. L0, we assume that it has a saddle point. Explicitly satisfy this condition. It has a minimum over x and z, if you notice, because we are assuming that f and g are convex. And well, in terms of y, it is a linear function, so we assume that it satisfies it. And in particular, we are not making any assumption on a and b. We don't make it to be a square or full rank or anything. Just assumption, this second assumption.
In here. So, can you go to the previous slide actually? Or the slide before? Okay, so if you go for L0, then what would be the update for xk plus 1? Then you wouldn't have any change because
You will not have this.
exactly. So then xk plus 1 would be exactly identical to xk minus 1 for all k. The same would happen for z, and the same would happen for u. So it means that you are not updating anything, right? By definition, because
That's like a 0 type step size, so you're not doing anything.
exactly
Yeah.
you're not doing anything. Those inequality would hold, of course, but I'm just saying that you're not doing anything actually, essentially, with L0, because it just doesn't make sense.
Because you again are not updating y.
You're not updating anything.
So yeah.
Oh, but I think they don't use
It
that
is the
in
same
practice.
method of
You're
multipliers.
asking like, why is it part of the proof? Why are they talking about it?
Exactly.
Maybe for analytical purposes. Maybe they want to use it to show something, but maybe like not as a basis to.
No, by definition, L0 doesn't make sense.
I mean, it's the Lagrangian of the.
But
I mean, it's
that's
the proper Lagrangian of the problem.
But L0.
Yeah, so
L0
it has a mathematical definition. But
Yes, it definitely it does have
Yeah.
a definition, but the thing is that you had some step size alpha k, and then you absorb alpha k to rho by saying that okay, we can neglect alpha k and then go for rho.
Right,
And
yeah.
now, since now you are saying that okay, there is a possibility to go for rho equal to 0.
No, we are not saying that. We're just using that L0 having a saddle point to prove the convergence. We will
That's
use
a
it in some
problem. I'm not
inequality.
sure for the augmented Lagrangian, rho should be always positive or it can contain 0 as well. So this is what I'm not sure.
Like,
Can
does
we
rho have to be
define
strictly,
L0? Exactly, it's
does
strictly
rho have to be
positive or
strictly
not?
positive? Yeah, I don't know. Yeah.
Because if
I mean,
it's not
actually, you
strictly-
could set to 0 because then if you set rho to 0, then you get back the origin Lagrangian of the problem.
Yeah, but
Right,
then the
because-
thing is that
yeah.
with this form of iterations, then you are
Not for
already
yeah,
at-
exactly. But I mean, definitely you cannot use it to build iterations because you're not doing anything to build an algorithm. But I mean, this would like L0. This would be like the. I mean, this would be the Lagrangian of the origin problem.
Yes,
So
yes,
Lagrange
yes,
of
yes.
minimizing of the original minimization. So the real Lagrangian that we get like from duality. Maybe I don't know. They could use it for like to prove something.
I don't know.
Yeah.
That was the first comment. The second comment is that if you go for L0, then U is not defined. So anything that you may work with, then it shouldn't
Alright,
contain
yeah.
probably U, because U by definition is 1 over rho multiplied by Y. So it's undefined for rho identical to 0. Just a note.
Yeah. Yeah, that's a problem actually. Yeah, because like otherwise, how do they define it? Yeah, that's.
You cannot be defined. The thing
Yeah.
is that the proof shouldn't contain U, perhaps. I don't know.
Yeah,
Let's see
maybe
the
there's some tricks.
This
Yeah.
one doesn't come from here.
Ah, okay.
It's based on the first form.
Mm-hmm.
Yeah, the results for group convergence. We need to show that the residual R, which was ax plus bz equal to c minus c equal to 0. That residual approaches to 0 as k goes to infinity. Next, we will show that f of x plus g of z will go to p star as k goes to infinity. This is the thing that we are actually looking for. And dual variable approaches to the optimal value. And, well, I can mention that this x neither u. No, yeah. If y go to y star, then u also need to go to u star. But x and z, they don't need to go to the optimal value. We just guarantee the optimality of objective.
Ah, okay. Only in the objective sense.
Yes, but
Okay.
in that paper, they said that, I don't remember whether they mentioned any reference or not, but they said that this can be guaranteed under some additional assumptions.
Right. Yeah.
Yes, the problems of ADMM. One of the problems that, the biggest problem is that ADMM is very slow. If you want to get high accuracy, accuracy means that how close we are to the optimal solution. And well, it is. But we can get sufficient accuracy for the application that doesn't need very high accuracy. It can be quite fast. For example, in my own work, I said something like I only use 100 iterations, and that works fine. And therefore, ADMM is much smaller than other methods like Newton methods. But for the case of our applications, larger scale applications of statistical and machine learning, ADMM works fine.
Sorry, do they have, maybe this is coming up late. So do they have like any convergence rate, like gradient methods, stochastic gradient methods? Do they have? No.
They should have,
Yeah.
but
Not in that.
not in this paper.
Yeah.
Not that I know of. I don't know. Sorry.
Yeah. no, just that. Yeah.
Yeah. KKT conditions. We're going to want to check optimality of this ADMM approach. We need to satisfy primal and dual feasibility. We need this residual to be 0, and the gradient, well, subgradient of Lagrangian over x and z should contain 0. So first, we start from the simplest one. By definition, we know that zk plus 1 minimizes this Lagrangian. So we can just simply write the subgradient of this. You will see this. This is the derivative of y times residual. You will get b transpose, and this is rho over 2 norm 2 of this residual. Again, you can write this by substituting the residual r, and you can see that y plus rho r is actually yk plus 1. So we are again satisfying condition number 5. Therefore, the optimality of ADMM results from the optimality of So it's also satisfying conditions 3 and 4, so that's what we should be looking for. For equation 4, we say that again, similar approach. We say that xk plus 1 minimizes the Lagrangian. You can write the same thing and do a little bit of mathematics. You will see this term. Now, we have one additional term here, which is this guy, compared to the optimality conditions, which is this. We want to show, again, we want to show that any pair of x, k, and z, x, z, and y satisfy these conditions. So this term actually should go to 0 as iteration goes ahead. So we again define this as another residual, dual variable, dual residual. We will show in the proof that this s and r, where is r, these two goes to 0 as ADMM proceeds.
One crazy
Yeah.
question. Why is it called dual residual? Is the difference between
Because-
zk and zk and z is primal variable?
Z is primal.
Z primal.
Yeah.
Why
X and
is
Z
dual?
is primal, yeah.
Exactly.
Because that is
Yeah.
dual feasibility conditions. Maybe that's why they call
Okay.
it dual.
Okay.
Yeah.
Okay, proofs. We assume that L0 has a saddle point, x star, z star, y star, and we define function v, a positive function, and we will show that v versus iteration is a Lyapunov function in the sense that it is a non-negative quantity that decreases in each iterations. If we can show inequality 6, this we will see the proof. If we can, sorry, not the proof. If we can prove this inequality, we show that vk plus 1 is smaller than v minus some positive value. It shows that actually v function is decreasing over iterations. If we can show this, then we can simply see that vk is positive and is smaller than v0, and these two terms are bounded. Therefore, by iterating these things, maybe I can write it. So, for example, you can write that v1 is smaller than v0 minus this term, let's call it, I don't know, delta 0. Then you can write v2 is smaller than v1 minus delta 1 as well, so we can write it v0 minus delta. Yeah, we can continue writing these things, and then we will see that, okay, y infinity is smaller than v0 minus this whole sum, which is the sum of from k to 0 to infinity of these terms that you see here. And then this guy is always positive, so we can take this guy to the other side of the inequality, you will see this. Straightforward. Okay, now I'm done. So if we agree that this is true, then we can, and the rest is just straightforward, we can see that this inequality holds, and therefore rk, each of these terms should go to 0, otherwise this will be unbounded. These two goes to 0, and this is actually a function for S dual residual.
One question. Why v0 should be finite? We didn't have that assumption. So essentially, why yk minus y star should be bounded? Do
We
you have an
assume that
assumption?
y star is bounded, no?
No, y star can be bounded or not, it just doesn't. The thing is that yk minus y star, assume that yk is infinity, y star is infinity, and yk is another infinity very close to y star, such that yk minus y star can be still bounded. I'm just saying that the things that you need to have assumption here is that v0 should be bounded, I guess. So meaning that
no.
Okay.
This has some value, and this is greater than 0, so it cannot. This guy here, it can be infinity, because otherwise it will go below 0. No?
I didn't get it. I'm just saying that
If
It's a
these
Lyapunov
two
function,
are
right?
unbounded, then this inequality will not hold, I guess.
this inequality is a direct consequence of being a Lyapunov function, right?
This is because of the definition of v,
Yes.
if it's possible.
Yes. And the maximum value for this v is v0.
Yes.
So the only assumption that you need to have is to have a bounded v0. But it's not in assumption 1 or assumption 2, right?
What
was the
assumption?
Can you go to assumptions again, sir?
No, this is obvious, but
And this is a condition
That's
only on
also-
f and g, so nothing on y.
but the first iteration is the minimization over f, I guess. This is 0, this is 0.
Doesn't matter. Just go for the definition of v.
Mm,
Definition of v is 0. In step 0, you don't have anything, right?
yeah.
So you don't update anything. You just randomly pick some y and randomly pick. This is just
No, they're
initialization.
0.
They could be anything, right?
Yeah, they should.
I'm just saying that that should be an assumption. That yk minus y star should be bounded and zk minus the star should be bounded. So the initialization of the algorithm should be within some bounded distance in terms of norm 2 distance. Some bounded distance with respect to the optimal solution.
Yeah, maybe I missed
Like I
something.
said, that
Yeah,
should
right,
be this
right.
assumption.
Yeah, exactly. I think that's also common. Like, I mean,
It's
that's also
pretty
like a
common.
common
I'm just
assumption.
saying that that should
Like
be
you don't start from somewhere that is infinitely far from the optimum.
exactly.
Yeah, that's reasonable.
You can start from that, but then and still you can have this Lyapunov function
Yeah, maybe
Well,
I have
there's
to
some
something in the
guarantee.
proofs, but
Yeah, exactly.
to go to the.
Yeah, exactly.
So yeah. So anyway, these two converge to 0 because of this inequality. Next, we need to show inequality 7 and 8. Inequality 7, we have an upper bound for p star minus pk plus 1. If we show that this is true, then r also goes to 0, so this approaches to 0. And if we agree that this inequality is true, again, r also goes to 0, this term goes to 0, so this whole thing goes to 0, therefore we have the limit pk goes to 3 star. So these are the three inequalities that we need to prove. We start from the simplest one, inequality 7, that you see here. We use the assumption that we have on saddle point level 0. We assume that this is true. We have a minimum point over x and z plane. So we can just simply write pk plus 1, this is the definition. And by using this inequality, we can write that, okay, this is p star actually. And what we have here is pk plus 1 plus this term. Because we're talking about Lagrangian at the point 0, so that row is 0. So if you remember, yeah, this. So we only have that guy, and this is what this will be y star times residual. Yeah, so we have this inequality, and you can just rearrange it, and you will get inequality in 7.
No, we can't.
Why?
Because there you have. Okay, now you have just r.
Yeah.
Just I should double check. Because the algorithm cannot be defined. At least the second algorithm cannot be defined
For
the case L0.
you're talking about that issue, yes.
Exactly. So here we are using the fact that L0 does exist. I'm not sure if L0 by definition can exist.
I mean, the equation for L0, yes, that does exist.
Yes, but
Yeah.
with this L0, those iteration may not does exist.
I mean, it doesn't have any algorithmic interpretation, but
Yes.
mathematically.
No. The thing is that I'm not sure even if we can define those algorithms mathematically. So that's the problem.
I think it's referring to the Lagrangian when you set rho to 0, right? I think this is what they're.
Yes.
Yeah.
But the
Yeah.
iteration over U, for instance, they are not defined.
No, they are not.
Yeah, but you don't need that. They are only referring to it's just the equation for the Lagrangian setting rho to 0. That's the only thing it refers to, I think.
It only uses
Yeah.
the L0, not the iteration.
Yes, but
Yeah.
then you are using xk and xk plus 1, so you should make sure that those
Okay.
xk and xk plus
Coming
1
from
are
that
defined.
algorithm.
X and x plus 1 come from another algorithm when rho is not 0, but L0 is just
Yeah.
the definition.
Exactly. That's also my impression.
Mm.
Yeah.
For
But probably
every
check,
x and
yeah.
z other than x star, so maybe, yeah. Makes sense.
Yeah, I mean, probably
Just the
just a construct that they need to prove something, but the iterates come from the case when like rho is non-zero.
Mm.
Yeah.
Okay.
Next inequality we again use this trick. We know that by definition xk plus 1 minimizes the sky, so we again write the subgradient. And you know that yk is by definition yk plus 1 minus rho r. So we can see that 0 is an element in this sky. Okay? This is just rearrangement of this equality. This implies that xk plus 1 minimizes this function. If you take the gradient of this function, you have an x, and this guy will be transposed. Therefore, xk plus 1 minimizes this guy, and we can see that we just substitute f star in here, x star, and xk plus 1, you will get this inequality. Straightforward. We will do the same trick. Here it was for x. We will do the same trick for z. You can see that z minimizes this. And again, I substitute z star and zk plus 1. I get these two inequalities. If we add these two and use the equality constraint, optimal equality constraint, you will get inequality in 8, which is this. There are a bit of mathematical computation, but yeah, you should see this. So, inequality in 6, this has something like 1-page equations. I didn't include it in here. There is no mathematical tricks or anything. This is just some mathematical summation and rearrangement. If you add inequality in 7 and 8, the thing that we proved just now, you will get these. And by some manipulation in this algorithm, in this equation, and rewriting it, you will see the equations in 6, which is this guy. It seems to be very simple to prove, but actually I tried, but I couldn't prove it. But anyway, this has 1-page proof. If you're interested, it's available here. So, yeah. Next, I'll just talk about stopping criterion. Well, from inequality in 8, if you remember, is this guy. You have this, and you can just, by some replacement here, you instead of rk plus 1, you will see that minimizing this function. So again, we can write the augmented Lagrangian here, just like as dual ascendant, we will see the summation. It is separable in xi.
Sorry, it's
Yes.
all applicable also for the complex values, right? Not only for real value
Yes,
systems, but also
I
complex
guess so.
value.
Yeah.
But it is.
I haven't seen anything like that.
But that's what
Yeah, it's mathematical equations, so big, but yeah, it should work. And yeah, Lagrangian is the sum of some separable terms in xi. Now, ADMM for this problem is similar to the dual ascendant method. The first part of the ADMM is over only xi. It is minimized. It is optimized in every individual node from 1 to n, and this is only one of those terms in the summation. The second part is minimization over z. If you take the derivative of this guy over z, you will not see this. You have a summation over this term, and this is quadratic, and you can clearly find the closed form solution. It's something like an average over updated value of xi and dual variable y. And again, you have individual dual variable updates in every node. So these two steps are updated individually in the processing node. We have a middle step, which is done in the center point in the network. So after optimizing this, every node needs to broadcast its own value or send it to the center node, then center node calculates it and then broadcasts it to the others. So this is the whole computational complexity that ADMM have, and that's a lot of based on my experiments, because we need a lot of iterations. We need something like 500 or 1,000 iterations, so you need to transmission. The transmission cost is a lot actually. And finally, one extension. There are some other extensions. I just have included one of them, which was most interesting for me. This is variant penalty parameter that we talked about. It can be, but they don't talk about, at least in this paper, they don't talk about the proof, whether it will be provable or not. But anyway, this works apparently in practice. The idea is that you can change rho k from iteration to iteration. The idea is that you have two residuals, that these two are supposed to go to 0. I'm just enforcing them to be not far from each other by a scale of mu. If r is much larger than s, let's say that mu is 10. If it is 10 times larger than s, then I'm increasing rho. This is some large value, bigger than 1, 2, let's say. I will make rho twice. Why? Because r is so big. And if you notice in the Lagrangian, where is it? Yeah. We have rho times residual. So if r is so large, then I can increase rho, then I'm enforcing r to be smaller. So if r is so larger than s, then I will increase rho. If s is so large, s by definition is rho times something. So if s is so large, I will decrease rho. That's the whole idea, and apparently it improves convergence. Otherwise, I won't touch rho. So yeah, this is one idea, but they didn't talk about the proofs, so I don't know. But apparently it worked on practice. So yeah, that's the end of the talk, and this was the paper that I found materialized. So thank you for listening.
Thank you for the presentation. Can I go to slide 25? This is way too high. Look at the differential bit. Proof of inequality 7. Be precise. Okay, so here you're using the fact that x star, z star, and y star is a saddle point for L0. Okay. Why is the case?
You mean by we have a minimum over xz plane?
Why this is a saddle point for L0?
We assume that L0 has a saddle point.
Yes, but you didn't say that x star, z star, and y star is the saddle point.
We said it.
No. You said that there exists some saddle point, and just for
But
notation,
because,
you use
because
this.
it's convex, yeah, but then because it's
Oh, I
convex,
see.
yeah, then that saddle point becomes the minimizer.
Okay, okay, we did have this
Yeah.
convexity. Okay.
Right? I don't know. This
Yeah,
is
I don't
this
recall.
Is,
Yeah,
that's
yeah,
the
yes,
intuition
yes.
at least.
You
as
said
far
we
as
did
I'm
have the
concerned.
convexity.
Yeah.
That's something like. Because there you
Yeah.
just assume that there is a saddle point. That's it.
It's not a strictly convex, but
That's okay.
Yeah. No, but I mean, like everything is convex. This is also part of like, I mean, everything is assumed to be convex. Yeah. So it would be also interesting to see what happened to the non-convex cases. Yeah, I think there is some work when because I mean most of the proofs that we have actually it's based on actually these like optimality conditions proving the optimality. It's all based on having a unique minimizer, which only is the case in convex cases.
Exists one, yeah.
Exactly. So whenever you go for, I mean, whenever this assumption is not true, yeah, it's interesting to see what kind of guarantees they would have. Yeah. Do they talk about that in the paper, like non-convex cases?
No, paper is just like overview paper.
Yeah,
They don't talk about so much detail or anything. This was the whole proof that they had. It's mainly applications.
No, yeah, I mean like another section. They have another section about like non-convex cases.
I guess the last section.
Right.
I didn't read. I guess.
No,
Yeah,
I
exactly.
didn't read it. It was
Yeah,
the
I
last
remember like the
section.
paper is like 100 paper. Yeah, it's like 150 pages or what? Yeah.
20.
Yeah, exactly. Yeah, so that's understandable. Yeah. Yeah, and then you mentioned that you had some applications in.
Yes, the
to
rest of the
neural
paper
networks,
is
okay.
based on the L1 norm minimization or quadratic constraint. For my own work, I'm using it on constraint least square problem that I just wrote.
Yeah.
And we solve it using ADMM because we found it useful and it's much
like
easier to work and tune the parameters. Gradient descent approach. Actually, I tried. Do you remember I tried that?
Yeah, exactly.
Propagation. I couldn't get it out of it.
Exactly.
It's the hell to tune the
That's
parameters.
much simpler. Yeah. And does it converge faster?
Yeah,
in practice?
it works pretty.
Yeah.
Yeah, I mean, tuning these, for example, tuning that row or
Yeah,
the number
sure.
of iterations, it doesn't vary a lot from, for example, application to application, case to case. But in gradient based, it's a little bit better.
Yeah, exactly. Exactly. Yeah.
Really? What's the difference? There shouldn't be any difference.
Yeah, because I mean here, I mean it's not a
At the end of the day, this is a gradient.
So my sense is that when you
gradient. Not sure actually. Yeah. So we go in the direction. I mean, it's kind of like, it looks more like primal dual decomposition or like coordinate descent method. So you solve a problem to optimality, and then you take the solution and plug it into the next problem. Yeah. So I don't know
Just
whether
breaking
this is,
down
yeah.
the whole problems.
Mhm.
It's a little bit like that.
Yeah, because you
Yeah,
have simpler
and
minimization, so
yeah.
you won't be so sensitive to those tuning parameters. Maybe that's why.
Yeah, but again, like, I mean, this is probably like a practical, this, I mean, this comes from a practical
But from
perspective,
convergence
yeah.
perspective, I can't see any difference.
No, exactly. No,
Theoretically,
from-
both of them should converge
Yeah.
if you have a convex optimization.
Exactly. Yeah. I mean, like when you have convexity, I mean, the proof is the same. Whether I mean, the proof is like
Yeah. For example, this ADMM, at least in my experiment, for example, this row, if you increase it so large, for example, I don't know, bigger than 10 to the power 5, it won't work. It will not converge. If you decrease
Right.
it to very, very small terms, to something like 10 to the power minus 8, it won't work either. So there is some range that it works.
right.
So
Yeah, sure. But then, yeah, but I mean, the range is already like pretty wide, right? Yeah. Yeah, but I mean, like as we say, like if you put the row to be like really, really large, then you're not. It should not work
but
even
in
in
the
theory.
proof, it should
Yeah.
work. I mean,
Yeah, in the proof,
you
but
can
even
see what's
yeah.
wrong in the proof.
In the proof, but then like the problem that you would be solving would be just with this one constraint. Yeah. So you would completely get rid of the part where you're doing the optimization of,
Yes.
of F. Yeah. Okay. Yeah. And this is probably like a nice segue to like this kind of distributed learning, these kind of problems. Yeah. So this application to consensus problems. Yeah. Yeah.